Hello everyone, here we'll be discussing partial derivatives, which can honestly be a pretty simple discussion depending how you want to cut it. Here I describe things in a pretty detailed manner, but then afterwards we'll describe it in a less detailed manner where we'll actually start to see some calculations, which will actually get calculus involved. So let's take a look. So we say if f is a function of two variables, then its partial derivatives are the functions f sub x and f sub y, defined by the following. Now, usually I just call it fx and fy. You could say f sub x or f sub y, but there's other notations we'll discuss soon enough. And these are the definitions of these partial derivatives. And if you take a look at them and compare them to the definition of f prime of x, it's very similar. Only we're adding h to the variable that we're subscripting here, and that's really it. So normally for f prime of x, we take the limit as h goes to 0 of f of x plus h minus f of x all over h. But here when it's derivative with respect to x only, we only add h to the x variable, everything else stays the same as with the normal derivative definition. Similarly, for f sub y, this is the derivative with respect to y, and now we add h to the y variable in this definition of derivative. Now I'll be quite honest, we won't really be using this definition really that much at all in this class. What we will be using really though are just what we know from derivative rules from calculus 1, but with this idea in mind. So the big picture here is you want to regard the opposite variable as a constant. So let me write that: regard other variable, or you can say other slash opposite variable as a constant. And we'll actually see that with some examples, but for right now, just kind of keep this idea in mind. Now, as far as notation goes, remember that for Leibniz notation for derivatives in one variable, functions in one variable, we use dy over dx, because y is f of x. But in this case, z would be f of x comma y. So you can say f sub x of xy, or just f sub x, is partial f over partial x. So this is kind of like our df over dx notation, but with partials. So this weird, I guess, curly D looking thing, sometimes people call this del, like del, which I think is a form of delta. It's actually not a Greek letter, believe it or not. In fact, I've only seen it really applied to mathematics. In fact, I really only see Greek letters in mathematics because that's all I really care about. But anyways, yeah, you can call this just partial. You could say del f over del x, kind of like df over dx. But I just say partial. So I'll say partial f over partial x, or I'll say the derivative of f with respect to x, or the partial derivative of f with respect to x. This right here just to me means partial derivative with respect to x of f of xy, or you can say partial z over partial x, or del z over del x. And the reason why it's z again is because just like y is f of x, z is f of x comma y. And very similarly for the derivative with respect to y opposed to with respect to x. So now here I give an example where we have this function given f of x comma y is 2x cubed y minus sine of x. And what I want to do, I didn't even write a description here or anything, but what I want to do is I want to find the partial derivatives. The one with respect to x and then the one with respect to y. So we'll use the subscript notation. So what do we think f sub x of x comma y is? Well, this is the derivative with respect to the variable x. So we're leaving, with this in mind, we're keeping the other variable y as a constant. So just imagine this y is joining this 2. Just like 2 is a constant, y will regard as a constant. So the derivative of a constant multiplied by x cubed is that constant multiplied by 3x squared, which is the derivative of x cubed by power rule. So 3x squared times 2 will be 6x squared, and the y comes along free for the right because we're keeping it as a constant. Okay, similarly here, this term doesn't even involve y, so it doesn't matter. Derivative of sine is cosine. And there we go. This is our answer for the derivative, partial derivative with respect to x. Now, with respect to y, let me kind of write that over here. I have a little bit of space for it. It's actually not too bad. It's a little bit to think about though. So remember, x in this case is now going to be a constant. So imagine x is kind of like 2 in the sense that the derivative of 2y would just be 2. So since x cubed is a constant, it comes around for free. Basically, you just drop the y. So this is just 2x cubed. Now what about this sine of x term? Well, since x is a constant, sine of x is also a constant. Imagine if x was the number pi, sine of pi would just be an ordinary number, and x will be 0. But even if it wasn't 0, its derivative would still be 0 because derivative of any constant is 0. So even though sine of x is a function with respect to x, in terms of y, its derivative would be 0 because we treat x as a constant in that case. So in reality, this term contributes nothing when it comes to the derivative of partial derivative of f with respect to y. So with respect to y, we just get 2x cubed. Great. So now we're going to look at some more complicated examples, and then from there we'll actually take a look at some interpretation of this when it comes to what it actually means graphically. Right, so for this next example, we want to find the partials of this function with respect to x and with respect to y, of course. So remember how we do that. For fx, let me just call it fx for the partial with respect to x, we're treating x as the variable and y as the constant, which is okay here because 1 over a number is just that multiplied. So imagine if this was like 3, 1 plus 3 is 4, and this x over 4 is just 1/4 times x. So really what we need to do is take the derivative of the inside by chain rule. So we're going to apply chain rule here. Derivative of sine is cosine. The inside stays the same by chain rule, and then we multiply by derivative of the inside. Derivative of any multiple of x, you just drop the x. So like derivative of 1/4 x, for instance, is just 1/4. So this is going to be multiplied by derivative of the inside, which with respect to x is 1 over y. Well, 1 over 1 plus y. So there we go, that's our first guy. And I don't really need to write this in any other way. I'm just going to leave it like that. That looks fine enough for me. The next one's going to be a little more tricky though, because I think we have no way around using the quotient rule. And let me try to explain why. So first off, yes, derivative of sine is cosine, that is certainly true. But now derivative of the inside, that depends, because now we're taking derivative with respect to y, not with respect to x. So now we're treating x as a constant, so think of this as just 1 over 1 plus y. So certainly the inside stays the same because of chain rule, but now we need to multiply by derivative of the inside, and here's where we have to consider the derivative of something over 1 plus y, because this x we're just treating it as a number. So you can think of it as 1, for instance, but you still leave it as x when you write the derivative. So we're going to have to use quotient rule here. So that's going to be derivative of the top, well, derivative of constant is 0, times regular of the bottom, minus regular of the top, times derivative of the bottom, which with respect to y is just 1, because derivative of 1 is 0, derivative of y is 1. So this is really just 0. In fact, if you take a look at this, this all really just simplifies to negative x on top. So I'll write this as negative x, if you don't mind, all divided by the bottom squared. And actually, just to make it look a little nicer, maybe we can pull the negative out in front. But you know what, just because I don't have too much space, I'm going to leave it like this. So we can kind of compare to see the real difference here. And it's kind of nice that we see they look pretty similar, but yet a little different. I still feel a little weird about that. I really would want to write the negative in front. This to me looks a little weird, kind of sloppy, but it's fine. I've gone over the concept, and that's really all I really care about for this example. For this one, this is a little different. So here we have this function of two variables, 4 minus x squared minus 2y squared. And we want to find f sub x of 1, 1, and then fy of 1, 1. And then from there, I'm actually going to interpret what these values represent. And they actually represent slopes, kind of like the derivative evaluated at a number represents the slope at that point, at the point with that x value. So we'll discuss that soon enough. So let's see. Fx, what is fx? Well, fx of xy is the derivative of this with respect to x. So y is a constant, derivative of 4 is 0 because it's a constant. This would have derivative of 0 as well. Derivative of negative x squared then is just negative 2x, and that's all that survives. Okay. Similarly, fy of xy is what? Well, here, anything that's a constant already is still a constant, and anything involving x only is a constant as well. Or just x is a constant as well. So here, 4 is a constant, x squared is a constant, but this is not a constant. So derivative of these two are 0 with respect to y. Derivative of 2y squared is 4y to the first power, so it's negative 4y actually. Great. And now we have to evaluate this at the point 1, 1. So when x is equal to 1 or when y is equal to 1. Because remember, inputs here are x, y. So when x is 1 and y is 1, fx of 1, 1 just becomes negative 2. Similarly, fy of 1, 1, well, y would be 1, so that would be negative 4. So here are our answers. And I want to interpret this, but it's a little hard to interpret this just because to graph this kind of a thing is a little difficult. But I'll try to explain the best I can. And basically, just imagine that we have our surface graphed in 3 dimensions. And if you want to use a graphing utility to actually see what it actually looks like, you can certainly do so. But it'll be some curve, something like this, imagine. Probably should be drawing it in red. But that's okay, I'm going to draw something else in red. So let's consider the point where x is equal to 1 and y is equal to 1. So this is the point 1, 1 on the xy axis. But then when you plug it in here, what do we get? Well, when x and y are each 1, you get 4 minus 1 squared, which is 3, minus 2, so that's 1. So actually we're going to have this point up here, which is the point 1, 1, 1. So this is really x, y, f of xy, if you think about it. Because f of xy is just z, so it's the z value you get when you plug in those xy values. So that part I think makes sense. But now, here's where things get a little weird. What negative 2 here represents in this context of the partial with respect to x is actually the slope of the tangent line in the x direction. So if you were to consider the x direction only, I'm trying to draw a dotted line here, kind of like imagine a slice in the x direction. So in other words, parallel to the x-axis, you'll end up getting this line here, and the slope of that line will actually be negative 2. Okay? Now, very similarly, if you were to do the same thing, I'm going to try to do it in green, but the colors may clash. Okay? If you were to take a look at the slice in the y direction, so that is parallel to the y-axis, so this dotted line represents that slice there, kind of taking a plane and cutting it through, then the tangent line passing through that point will have a slope of negative 4. So it should be steeper, but in the same direction. Now again, if you actually graph this with a graphing utility like Quick Graph, like I've shown on a few videos ago, you'll actually see exactly what I'm talking about. But, well, kind of. It is still a little much to take a look at this. But yeah, that's what these represent. Just basically tangent lines, but at a certain angle, basically. So in that x or y direction, which I think is fairly intuitive and definitely makes sense. So it makes me happy from a calculus perspective. So now what do I want to do? Now I want to discuss not multiple variables, but I want to discuss higher derivatives basically. So taking derivatives beyond just the first derivative, but considering partial derivatives. So let's take a look to see what that's all about right now. Right, so before we actually get into higher derivatives, let's actually discuss a little something a little different. So what if we had more than 2 variables? So this function of 3 variables, for instance, can we find the partial with respect to x, y, and z? And of course we can. And the idea is very, very similar. You just set all of the other ones that are not the subscripted one as constants and take derivative with respect to only that variable. So that's the main idea behind anything that has a higher amount of variables than just 2. So for instance, fx of x, y, z will be treating x as the variable, everything else is the constant. So ln of z is just a constant multiple of e to the x times some constant. So really this reminds me of something like 3e to the 5x, because ln of z is representative of 3 and y is representative of 5. These are just constants. Derivative of this is 15 e to the 5x. So this is kind of what I think in my mind, just kind of imagine where these things move around. So derivative of e times a constant is itself. So I guess we could, and you can write it really in any order. So I'm just going to write it like this in the same order. So the constant comes out for free because it's a constant multiple of the function. And then by chain rule, we have to multiply by derivative of the inside. Derivative of this power x times y with respect to x is just y itself because the x drops basically. So it's this times y. I don't want to write y here because it looks like it may be in front. So let me write it as y times ln of z if that's okay. That I think is an okay way of writing this. So this is f x, and now let's move on to fy. Let's see if we can get this idea down. So fy, the partial with respect to y, now y is our variable, but x and z are our constants now. So you know what, this is actually symmetrical in some sense, because x and y kind of interchange. So in reality, this is going to be derivative of e to anything times a constant is itself, but then derivative of the power xy with respect to y is just x, because think of x as a constant, derivative of a constant times y is just a constant itself. So the x drops down, ln of z comes down for free because it is, well, constant, and there we go, that's f sub y. So it looks super similar to f sub x. Let's see what f sub z looks like. Maybe it looks similar, maybe it doesn't, who knows? You don't know until you actually try it, I guess. Let's see. So here z is our constant. Oh, look at this. I'm sorry, z is our variable. So xy is our constant. That means e, which is a constant to the x times y, is also a constant. A constant times ln of z has derivative, that constant times the derivative of ln of z. Derivative of ln of z with respect to z is 1 over z. So this is actually the constant e to the xy over the variable z. Wow, it looks a little different. Perfect. So that's it for this example. Now we can move on to higher derivatives. In fact, we'll mainly be talking about second partial derivatives here. And there's a different notation we could use. We could use the partial notation. So first let me describe, this is fxx, fyy, fxy, and fyx. These are all the different ways you can take the second derivative depending which variable you take first then second. So here x first and then x second, y first and y second, x first and y second, y first and x second. Now I'll just give you one example. So let's imagine fxy, the partial notation of this with del's would be partial f over partial x partial y. In fact, it's really del squared. And the reason being is because with each subscript you get a del in the numerator. So imagine this right here, fx is del f over del x, and then taking with respect to y, now we get another del over del x in front, so we get two del's on the top here. So similarly for fxx, this would be del squared f over del x, which you could just write as del x quantity squared. But anyways, that's just the partial notation, which is kind of equivalent to, again, this Leibniz notation. So now here we want to find all of the second partial derivatives of this function. Let's see, let's take a look. So first we need to find, it's a little bit of work because first we need to find fx and fy. There's no way around that. In fact, I hope we have enough space here. But fx is going to be, I'm not going to write the xy because this is too much to write. So I'll just write fx for short. So fx will be 3x squared for the first term. Derivative of x squared is 2x for the second term. Y cubed is a constant, so that multiplies for free. 2y squared is a constant, so that just drops. Right, good. So that's fx. What about fy? Well, fy, that's a constant, so that drops. Here, x squared is a constant, that comes out for free. Derivative of y cubed is 3y squared. So this will be 3x squared times y squared. Derivative of y squared is 2y, so it's going to be negative 4y. Perfect. Now these are the first derivatives, now we can find the second derivatives. So for the second derivative here, we can take fx and then x again. So now derivative of this with respect to x, derivative of the first one becomes 6x. Derivative of the second one with respect to x, the x drops, because derivative of 2x is just 2, and y cubed is a constant, so it comes down for free. So we get plus 2y cubed. Then similarly, we can take fxy, which is the partial of fx with respect to y. So this with respect to y is a constant, its derivative is 0. Y cubed with respect to y has derivative 3y squared, which multiplied by 2x is 6xy squared. Perfect. And now, similarly for this one, its derivative with respect to y is, let's see, so again, 3x squared here is a constant, derivative of y squared is 2y, multiplied by 3x squared is 6x squared y. I think that makes sense. Derivative of 4y is just 4, so it's negative 4, with respect to y, remember. And now finally, derivative of fy, but now with respect to x. So here, 3y squared is a constant, x squared has derivative 2x with respect to x, so it's going to be 6xy squared. And derivative of 4y, look at that. Derivative of 4y is 0 because 4 is a constant with respect to x. So we can compare these if you want. And these are our 4 answers. Now what you may notice is that, look at that. fxy and fyx just so happen to be the same. So you may be asking yourself, will they always be the same? You can do a few examples yourself to see if that isn't the case. It kind of is, and we're going to talk about that right now. Alright, so this is where the video actually starts to come to a close, and the last things I want to talk about are these, starting off with Chloro's theorem, which just summarizes what we saw in the last example, that fxy is equal to fyx. Of course, this only happens in certain cases, and here's when it happens. Supposing that f is defined on a disk D, so just some open interval. I guess it could be a closed interval, but just some, not interval, but some domain D on the xy plane, containing a point A, comma B. If fx and fy are both continuous on this domain, or on this, in this set, then it is true that fxy of AB and fyx of AB are the same. They have the same value. Okay, I'm not going to do an example of that because we kind of saw one in the previous example. And now we get into partial differential equations, which I'm not going to do any true example of. I'm not going to show you how to solve those. I'm just going to mention them and say that they're certainly a thing. Just differential equations, only considering partial derivatives as part of your equation. So one example is Laplace's equation. So this is the second partial derivative of u with respect to x twice, plus the second partial of u with respect to y twice, where u is a function of x and y. And here, u of x comma y is known as a harmonic function. That's just what it's called. Not unlike harmonic series, it's just coincidence we're using the same phrasing here. Kind of like tangent function and tangent line, totally different. We're just using the same word coincidentally. So it has nothing to do with harmonic series. And as it turns out, u of x comma y is an example of this. So this is a solution to Laplace's equation. So in other words, u of x comma y just so happens to be a harmonic function. And if you ever take a class in complex analysis or calculus over complex numbers, harmonic functions actually come up quite a bit. And it has to do with taking derivatives of functions over complex variables, which is something beyond this class, believe it or not. But it's something that where this kind of makes a reappearance. So I'm going to show this real quickly though. So let's take uxx. So ux is going to be derivative of e to the x itself. Sine of y is a constant with respect to x, or in regards to x. So then that means uxx is again e to the x sine of y. So that wasn't too bad. But what about uyy? Well, uy, here e to the x is a constant, so that comes out for free because it's a constant multiple. Derivative of sine of y is, cosine of y with respect to y. Then uyy, derivative of uy with respect to y. Derivative of e to the x, e to the x is a constant multiple, so that comes out for free. Derivative of cosine, notice, is negative sine. So this is equal to negative e to the x times sine of y. And look at that. These are negatives. They're not the same, but they're negatives. What that means is that this is certainly true. If we take the sum of these two, the partial of u with respect to x twice and the partial of u with respect to y twice, and we add them together, we indeed get that it's 0, confirming that u indeed is a harmonic function. So that's nice. That's all I'm going to say as far as that goes. And the last example of a partial differential equation would be what is called the wave equation. That has to do with modeling waveforms, so motions with waveforms, whether it be ocean waves, sound waves, light waves, for instance. I'm not going to talk about it because I don't know too much about it, to be quite honest, but I do know that it is indeed a theme. I know there is another equation called the heat equation. I don't know much about that either. In fact, I couldn't find it immediately in the book, but I know that it is a partial differential equation, I believe. Don't quote me on that, but I'm pretty sure that is indeed the case. Alright, so that's all I wanted to say as far as partial derivatives go. One honorable mention would be partial implicit differentiation, which is something you can talk about, which is where you take derivatives of equations implicitly, but with respect to only one variable, leaving the other ones as constant. In other words, partial derivative. The book discusses a few examples, but I'm not going to discuss that. I think that's too much of a sidetrack, if you will. But anyways, with that being said, hope you enjoyed this video. I'll see you in the next videos. We'll discuss more calculus in 3 dimensions, where this will actually be used later on. So that's going to be a lot of fun, like always. Hope you enjoyed this, and I'll see you then. Thanks for watching.